Hey everyone, I'm going to give a quick video tutorial on hashing and some of the properties of hashes and why we use them. So first off, what is a hash? Well, a hash is one of those things we use all the time in cryptography. It's where you take a message and you put it through some kind of function, and then the output, it's called like a hashing function, and you get some like fixed output that's usually a little smaller. And we all know what it kind of looks like. This can be anything you like. This can be an article, your password. And this out here kind of looks like this. It's like gibberish. That's a 5KD7. So yeah, hashing is used everywhere. Often it's used for storing passwords in a database. Also used in message authentication codes. Very important thing. And let's first off, people sometimes get confused. So let's look at the differences between hashing versus encryption. I encourage you to pause the video and see if you can come up with 3 differences between hashing and encryption. So pause the video now. Okay, you didn't pause the video. Fair play to you. Let's have a look at some of the differences. First differences between hashing and encryption, right? They both take in like an input and they have this gobbledygook output. But one of the key differences is that a hash is usually non-reversible. In fact, it's a bad hash if it's reversible. We'll learn about that in a second. So first thing is it's non-reversible, because if I'm giving you my password, definitely don't want you to be able to go back to the original password. You know, you hash it, store it in a database as the hash. We definitely don't want you to be able to go backwards and find out my password. Second property of a hash is its fixed length. Encryption, if you encrypt a little sentence, it'll be about the same length as a little sentence. But if you encrypt the entire dictionary, you're going to get an entire dictionary's worth of encryption. Hashes are different. Even if you hash a single word or a single full stop, the output is always going to be the same length. So it's a fixed length output, usually like 128-bit or 64-bit, depends on the hash. Third difference is usually it's non-keyed. Encryption usually always has a key. That's the whole somebody's law, that you want to put all the secrecy in a key. Hashes don't have keys. You can do a hash document and then just append the key and hash it, but the hash itself doesn't really have a key built into it. Whereas AES document as a parameter just takes in a key. It's very important. That's how it's designed. Hashes just don't have that. It's just a set algorithm for reducing a big thing to a smaller thing. So that's basically explaining hashes. Let's talk about some of those important properties of hashes. So the first probably annoying thing about hashes you've learned, right, is first preimage resistance. And what does that mean? Well, it means given the small thing, it should be really hard to get the big thing back. That's a whole bunch of really complicated, confusing words to basically mean that a hash shouldn't be reversible, which makes total sense when you think about it, because if I'm giving you my password on a server, I'm hoping you hash it and never actually store my password, because I don't really trust you. And if you can take my hash, steal a password database, and reverse it into my password, that's very dangerous for me. So let me draw this in diagrammatic format. Maybe it will help explain. So basically, first preimage resistance is saying we have the hash, like a normal hash, just so we're familiar with the diagram. You take the message, put it in a hashing function, and it gives you this. So that's the normal hashing. Under a first preimage model, what we're trying to do is I give you the hash, you've got that, and what it should be it should be really difficult to go backwards and figure out which document, this is a question mark, caused that hash. So it should be really hard. Let me just make this emphasis. should be really hard to reverse. So this is the hash of my password down the bottom here. Down here, it should be really hard to go backwards. So that's the first preimage resistance. Given the small thing, given the hash, it should be really hard to get the big thing to go backwards. Hashes should be hard to reverse. That's the first preimage resistance. So let's talk about the second preimage resistance. That's where I give you both. I'll go to my favorite blue pen. I'll give you the original message. This time, you're not looking for the original message. I give it to you, and I give you the hash. And this time, it should be really hard. So here it is. You've got the small thing and the big thing. Should be hard to find another big thing that hashes to the same small thing. So that means I give you this. I give you the hash. You can compute that. That's totally fine. In fact, I'll get rid of the circle. Everyone can do that. Everyone knows the hashing algorithm. But it should be really, 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 really hard to find another document here that has the same hash. Should be impossible. It's not impossible, but it should be really, really hard. No, forbidden. Should be hard to find one. So second preimage is characterized by having the original document, having the hash. It should just be very hard to find another document. Why this would be important? Well, hashes are used for things like MACs, right? Message authentication codes, which give us integrity, gives us authentication as well, but we're more interested in integrity in this case. And say you're the, let's switch to a newspapery color. Well, let's switch to black. Let's say you're the Sydney Morning Herald, and you write an article that says, Adam is the best. It's a very, very short article because it's not very in contention. You might want to issue with it a hash, so people can verify that the article is correct and you've signed this hash or something to make sure that only you've done it. What would be a real problem, like the Sydney Morning Herald doesn't mind so much if you can go backwards. They don't care about first preimage resistance because the message is not really secret. They publish it publicly on the internet. They print 1 million copies of it every day and put it on our doorstep. They don't really care about that. But what they do really care about is second preimage resistance. They really care if somebody were to come along and maybe evil red pen and write something like Adam is the worst. Oh no. The Sydney Morning Herald would be very concerned if you could find, you could create a message that said Adam is the worst and change it as necessary until it had the exact same hash as this original real document. So this one's from the Sydney Morning Herald, and this one's a fake one. So the Sydney Morning Herald really don't care about you being able to reverse the hash, but they definitely do care about you being able to find another message that has the same hash as the original thing. Because what this over here is fake news. And they do not like that. So that's why second preimage resistance is a really important property, and why it would matter to some people over others. So that's second preimage resistance. Let's talk about the final one, which is collision resistance. Collision resistance is like a kind of generalized case of the one that we saw above. So collision resistance is, take any two messages, right? I don't know which one this one is. Oh, that should be dotted. And this one here, and another one. We know they're going to hash to a particular message. It's going to hash here. It should be really difficult, is what the collision resistance property says, is that these should not be equal. It's not quite possible that these will never be equal, like that's going to happen, but it should be really hard to find two things with the same small thing. To find two messages, two random messages, any random message, that when you hash them have the same hash. And that's about collision resistance. Here it says it up here, should be hard to find any two large things that have the same small thing. And when you think about it, all hashes, like you have all possible, just gonna try and explain maths here, so you know it's gonna end badly. We have all, this is like infinity, right? This is all the possible things in the world that you could hash. And hashes, because they're like 64-bit long, like there's a fixed amount of things. So you're gonna get like these duplicates where multiple things in infinity land here are gonna hash to the same thing. So imagine these are different words in the dictionary or whatever. Maybe I'll use different colors. You're just going to get multiple things hashing to the same thing. They're hash collisions. What we really want for the best hash is it to have like an even distribution. So you can see how like all these different colored dots here in different areas. And we want like, this is a really disgusting diagram, but we want basically all these dots here, you know, where they've landed in the same thing. That's like where they've had a hash collision. We want that to be spread out as possible. So like if I do draw this as a graph, which also might go horribly wrong. Let's say this is hash 1, hash 2, hash 3. And if I just list all the hashes all the way over to hash 2 to the, say it's a 64-bit long hash, just list them all out here and I do a frequency count. We basically want all the hashes to basically have the same frequency. Because that's going to give us the most, get rid of that, give us the most hash resistance. You can see how this frequency is just, you know, roughly it's all the same. So anything I hash, like hash potato, that's funny, has an equal chance of landing here and an equal chance of landing here, equal chance of being this hash and equal chance of being this hash. That's a really good hash. The bad ones, let me just draw one here, where the frequency distribution might be really out of whack. So like there might be a bias towards this particular hash, and then like barely any hash here. So if you draw that curve, most of the hash is going to be 1. So you're going to have a lot of collisions that occur on hash 1. So like in Facebook, for example, there is a password for your Facebook account, right? Like that gets hashed in Facebook. There is another word that exists out there that will allow me to type it into Facebook and log into your Facebook account. And it won't be your password, but there's actually an infinite number of different words out there that I can type in and they will result in the same hash as your password and allow me to log in. But they should be really, really, really rare to find. And the way they're rare to find is if all these passwords of all the Facebook users are evenly distributed. Because if most passwords on Facebook are hashing to the same password, like hash 1, whatever that is, then that's going to be really bad because eventually it'll be quite easy to find other words that collide with that. That's talking more about a second preimage resistance, where we know the password and we know the hash, trying to find a matching one. But the collision resistance talks about this general property. This is a generalized case with the second one. So if I could summarize these resistances as a little diagram, you've got first, this box is a little hash, and you've got the hash, and you've got the input. For first preimage resistance, should be really hard to go backwards. That's first. For a second preimage resistance, you have message 1, which goes into the hash, gives you hash. Should be really hard to find a second one that also gives you hash. And for third preimage, it's collision resistance. It should be really hard to find any 2 random inputs that hash to the same output hash. Okay, so I'm going to really quickly give a demo of a hashing algorithm so we can see these properties in action. So let's say we have a really bad hashing algorithm. It's my favorite hashing algorithm. It's called the atom hash. And the atom hash is really simple, and it makes for a really bad hash. Because what you do is you just take a word like, I don't know, computer, And to hash it, all you need to do is you just remove all the vowels. So this becomes CMPTR. Can you see that? How I've just removed all the vowels from the word? This is my hashing algorithm. So if it's a dog, hash of dog just becomes DG. This is such a bad hashing algorithm that it doesn't even have that fundamental property of a hash that it's a fixed length. So that's how bad hash it is. But let's do some examples with this hash. Let me show you one of this example. So let's say we want to do a first preimage resistance attack. Let's say we were given this word, which was the result as a hash. So let's say we're given the word PZZ. So this has had the hash function applied to it. It's had all the vowels removed, and we're given this hash. So a first preimage resistance attack is to figure out what word it comes from. And I'll let you into a little secret. This is quite a tricky one to reverse, right? What kind of, can you think of a word where if you put vowels in here somewhere, that it'll return an English word? Well, I know this word because I made it up. The word is pizza, right? Can you see that? So if you remove the vowels from pizza, it becomes PZZ. So right there, what we did there was a first preimage attack. And you can probably see now that it's quite easy. You probably could have guessed that. You could have probably brute forced it in a dictionary. Quite easy to reverse that one. So that's a first preimage attack. Let's see if we can do a second preimage attack. So a second preimage attack would be, given that we know pizza, and we know that it hashes to PZZ, the second preimage attack would be coming up with another word that when you remove all the vowels, hashes to PZZ. Can you think of an example of a word like that? Have a think. I've got one idea. What about the Italian word for square, piazza? Can you see there how we've come up with another word? So we knew pizza and we knew PZZ, and what we were trying to do was come up with another word that also hashes to PZZ. So quite there, what we did there, I'll just move my face down here, is we did a second pre-image attack. And we can try and do another second pre-image attack if we like. What about so what you kind of want to do, what helps is it's a lot easier than the first pre-image attack because you have these existing words here. Like we had pizza, so we just tweaked it one by adding an extra letter, right? So let's do that again. Let's just tweak it. And I know the Italian word for multiple pizzas is pizza, and that's another hash as well. So we've got another collision, and you see that's us mounting our second pre-image attacks. So we're using this hashing algorithm where we just remove the vowels. What's an example of a collision resistance attack? Let's do a collision resistance attack. Well, in that case, if we wanted to do that, we'd have to think of any two random words in the English alphabet in the dictionary that when you remove all the vowels from them, result in the same hash. And this is really easy to do. You can probably think of a few words yourself. A few words. I'll give you an example. Look at the word at. I bought my phone at the store, and I'm going to the zoo. When we remove the vowels from these letters, they both end up as T. So right away, we found a hash collision. And I think this is quite an easy one. This one is actually the easiest to do. You can probably think of a few examples yourself. I've got one here, another one. Write one down if you've got an example too. But another hash collision where they have the same hash is tip and top. When I remove the vowels from this one, they both hash to TP, toilet paper. There you go, lots of fun. And another one, just because I've got so many. One word. What about, here's a fun one. Tree and true. I climbed the tree. Yes, it's true. Both of these hash to TR. So you can see here, it's so easy to find collision collisions that occur, especially when you've got a really bad hash like the Atom hash is, quite a bad hash.